So once we know that, once we know the graph is solvable and we know for how many positions we can perform the exact synthesis, creating the design equation is easy. We saw how to do that, right? But let me just summarize and put all that. So synthesis process. Summary. And of course, the same thing that we are doing now for graphs with a tree structure is true for any serial chain. It's just a graph with a single branch, right? So first we define the topology. So this is the kind of structure we want to dimension. Second, we check solvability. Actually, let me put the intermediate step. The way we are doing it right now, we are simplifying everything to serial chains. So we reduce, right? Reduce. So that if we have loops, we take those serial chains that are equivalent to the motion of the loop, right? Then we check solvability on the reduced graph. We know how to do that. And at the same time that we check solvability, we compute the maximum number of positions. Compute maximum number of positions for exact synthesis. All right, now if it is solvable, then we write, if solvable, let's say for m positions, now we can write the design equations, which are just create the forward kinematics of relative displacements for each of the branches and equate to the position that that particular end effector needs to reach. Write design equations. Well, I guess we need to define the task too, somewhere. Well, once you know the number of positions, let me put here, define the task. So for instance, imagine you had a whole trajectory for each fingertip. Okay, you had thousands of poses because you are doing this motion, and it turns out that your particular hand you are designing for is solvable for 20 positions. You have to downsample that whole trajectory and take just 20 points along that trajectory. That will be the definition of your task. Now, once we define the task and we know the number of positions, we can write the design equations. And remember that those were just the product of exponentials, which give us screw displacements about each joint, and then we multiply all those, we get relative displacement from a reference configuration. Okay. Write the design equations. So we have the product of exponential delta theta I over 2 Si I equal 1 to Ki. These were the common branches. Product of exponentials delta theta from Ki plus 1 to Ni delta Ij Sij equal to P, okay, 1K. So a lot of indices, and I'm going to put this here. There is not a point, it's a whole displacement from our reference displacement, which is number 1, to any other displacement. So K goes from 2 to M, and here we are assuming we take the first one as the reference where we will be based all our motion, the first position of this M, and then we have J number of branches equal 1 to B number of branches, and then sorry, I1 to KI, this is not right, K, this is KJ, right, and NJ. Hello. Yeah, so for each branch we will have a number of common joins and then a total number of joins. So let me just, and IJK may be different here from our standard notation, but let me just put that with branch J has KJ common joins and NJ total joins. Okay. So these are the design equations. This is the easy part now, right? So if, depending on what kind of algebra we are using to express our displacements, we will have more or less elements here. But we know that our 3D space is 6-dimensional, so there will always be 6 that are independent. If you are talking about matrices, you have a 4x4 matrix, right? But the last row is 0, 0, 0, 1. So you have 12 elements, but only 6 of them are independent. If you have a dual quaternion, you have 8 elements, but only 6 of them are independent. The number of independents will always be 6, because that's the dimension of our space, okay? But depending on what algebra you use, then you will end up with more or less equations. Many times those extra equations help the convergence of the numerical solvers, right? They are giving you extra structure. So if we use dual quaternions, which is what our solver does, if we use dual quaternions, then we'll have, this will be 8 dimensionals. We have 8 times the number of positions minus 1, m minus 1, times the number of branches, B equations. There is a high number of equations. They are very highly nonlinear. I mean, all these are unknowns, remember. All the coordinates of your joints, all your angles. So if you have, for instance, I don't know, 5 joints, you will have 5 numbers here multiplying times the joint variables. So these are highly nonlinear. There are a lot of people working on how to solve these systems of equations. We are among those people. We are following several strategies. On one side we have a numerical solver, which is working fairly well. It's solving very big systems, but of course it gives us only one solution at a time. We are working on other approaches. We are working on Grosvenor bases. We are working on interval solvers. So we have several lines open, but for these big systems, so far it seems that numerical solvers are the only way to go. So how do we solve this system? So here we have the whole process, right? Define topology, reduce, check solvability, define the task based on the number of positions. If it's solvable, create the design equations, solve the design equations will be the last point. Solve the design equations. Let me just extend this. Design equations to obtain, what are we going to get out of this process? Well, what we are getting is the dimensions of our system. But the way we are obtaining those dimensions is what we will get is the configuration of our system at the reference configuration. That means the location of the joint axis. So coordinates, they are lines, so they will be lines in space. Coordinates of joint axis at reference configuration. Remember that what we call the reference configuration is the first position. You can take any position, m equal 1. And in addition, because they appear here, we obtain the angles for reaching those positions that we have defined. That's an extra. That solves at the same time the design problem and the inverse kinematics problem for those particular positions. So we get the joint values to reach each position in the task. Okay. Coordinates of the joint axis, joint values to reach each position in the task. We really don't need this to define our system. This is an extra. So one of the things we have tried in the past is eliminate all these extra variables to make systems with less variables, equations with less variables, but that increases the degree very, very much. So far we haven't been successful on eliminating those. Alright, so how do we solve these equations? Very nonlinear, a lot of variables, a lot of solutions. We use our solver. I'll go to the next page for that. Our current solver is called Artrix. I think this one is capital and the other is not. Artrix. Funny name. Articulated tree kinematic synthesis. And it's written in C++, and it's a combination of a genetic algorithm plus a Levenberg Marquardt kind of Newton solver. Okay. Okay. In addition to this, we have an interface. It has a Lua interface. So that we don't have to really create the design equations every time. It's kind of tedious because you will have to, if you do it by putting the set of equations directly in this algorithm, you will have to create a file which will be different every time because your positions are there, the desired task you want to reach. But really, to create these equations, it can be done automatically because once you know the joints and the type of joint and number of joints and the connectivity between those joints, you can create in a systematic way the forward kinematics and then just equate to the task. And that's what is done here. So in this Lua interface, you just have to enter the topology, and then you have to enter the task, what positions you want to reach, And this solver accepts positions, velocities, and accelerations. We haven't talked about those, but you can. Maybe let me say something about this briefly. So for instance, if you're counting, when you count for the maximum number of positions, if you get, for instance, m equal 5, you could do 5 positions, or you could do 3 positions and 2 velocities, or you could do 3 positions, 1 velocity, and 1 acceleration. But for the position that you define the velocity, you need to know the position. Okay, you need to know, I want this velocity at this point. So you cannot just define I need this velocity somewhere in the space. You could, but it really doesn't make much sense to do it that way, right? So we can define, for instance, we can define, let's say, position 1, position 2, position 3, and then we could define velocity 1 and velocity 2, for instance. That would be 5 positions, for instance. So you create a Lua file, which is fairly simple. You can just create it as a text file where you define the topology, and you enter the task there, and then you just run it, and it will give you the solutions. Okay, so that's a fairly straightforward process. Right now we have Artrix installed in my computer, so you can send me your Lua file, and I'll send you your solutions back.
How are this a normal 3D point, or the point how?
I'm going to show you the Lua file now. So we will, after knowing this process, now we will go to the Lua file. We will try to know what each command does there, more or less, and then you will be ready to start using it. Okay. That's it. So we are done with this. You can do the dimensional synthesis of any serial chain, or any tree chain, or any closed loop chain in which it's okay to reduce it the way we do it. So basically, eliminate the branches, leave just one of the branches that has a similar motion. It has the same linkage locus space, remember? All right, so let me show you the Lua file. Here it is. So this is our Moodle page, and I posted a couple of Lua synthesis files here. I don't know if I double click. I guess that works. Yes, doesn't let me. Okay. So this is the Lua file. Can you see it well? Yeah. Okay. So these are some of the files that it requires. So file save, here you need to put the name of the file where you want to save your result. Okay. Change this, because if everybody gives me the file with this, you are going to overwrite somebody else's output. Okay, so just put your name there, or some way that I can identify that this is your output. Okay. GA options, these are the options for the genetic algorithm. Okay. If you don't like, we are right now working with this, and it seems to work fairly well, but you can change that. Now here, this is a function to generate random values for velocities in your positions. If you don't know what positions to pick because you are just testing the algorithm, then generating random values is the best option, because then you can make sure you are not going to a particular type of dependence between the positions. If you try to generate them randomly yourself, normally they fall on a line or on a circle or something like that. If you really want something random that will give you the most general case, just define them randomly. So here, this is what this one is doing. And now, here is where we generate the topology. So this is the topology of this robot. And right now it's saying, so this which we will have to modify to make more complicated trees. This is not going to work for our trees that we are defining, the complicated ones. This means two joints, two revolute joints. Right now it only takes revolute joints. Two revolute joints common, okay? Two common revolute joints, and then two branches with one revolute joint each, okay? That's what this means. For instance, if we want to create a robot with, oh, I cannot modify it here. I should, yeah, let me just save it and open it somewhere else. Okay, yeah, that's better. All right, so we'll erase all this. Okay, so we were able to use a, okay, so this, if we want to put, for instance, a robot with 3 joints at the wrist, so we put 3, and then we want 5 fingers which have 4 joints each. 1, 2, 3, 4, 5. Okay. If we want a serial chain, then we would do just n equal to, for instance, if it's a 5 serial chain, you could put 1,4 or 4,1 or something like that. Means one single branch with this many degrees of freedom. Okay. So this is right now, it's not prepared to handle several branching. We need to modify that. Like the example we are doing right now, which has, you know, a first branching and then a second branching. It doesn't, I don't think we can handle this with this notation, so we'll need to modify it. All right. So then it computes here the number of branches, which is the number of these minus the common ones, so n minus 1.
So once again, 2, 1, 1 is for n, that means
this is the topology.
Yeah.
So 2 common joints and two branches with 1 joint each. So the number of elements of this array is the total number of branches plus 1, which is the common ones. Okay, so that's why we define the number of branches as this minus 1. And then here you define, it's not calculating it automatically. We know there is a formula and we need to implement that. That's another thing. All this I'm pointing to Ali, so it's going to be very busy. We need to implement that right now. You have to do the counting by hand, see if it's solvable or not, and then decide how many positions you want, how many velocities, how many accelerations. They have to add to the number m. Okay. Here we have again the random generation of the values. Okay. So random G, random vel, random vel. Okay. Right now this was for accelerations, but we are not using accelerations here. We are using just velocities in this particular example. Okay. So this is all random generation. Instead of this, you could put your Pij equal to some values, and this takes dual quaternions. That's the way it's prepared. So your positions will be transformations expressed as dual quaternions. And remember, you have all those mathematical functions that given a point and angles, and you know, you can create your quaternions very easily. We have those functions that will do that, and we will go over those maybe if we have time. So here your transformations written as dual quaternions will be your positions, and the velocities are written as twists. Okay, so using the Lie algebra. So angular velocity of the body and linear velocity of a point. That point is the point that coincides with the fixed frame right now. We may modify that. Okay, so it's a point instantaneously coinciding with the origin of the fixed frame. Okay, the velocity of that point, because we are using, you know, that twist in the fixed frame, Jacobian. All right. So here we define the positions, and then this just generates the output. And from here on, we don't have to modify anything. What it is doing is calling the solver, you know, opening an object of that type of the synthesis, calling the solver, computing the elapsed time, and you know, writing the data to the file. Okay. So this from process on, or from create output on, we don't have to touch anything if we don't want. You can change things here, of course, if you want. and that's it. So basically define your topology, define your indicate the number of positions, define your positions, and it will give you your answer. Okay, let me show you another example. So this particular 2113 seems that it was solvable for 3 positions. Let me show you the other one example that I put in here. Okay, we can look at it here. This is a 3R serial chain. Okay, so we have 2, 1, which means 2 in the common joint, 1 branch. So that's a serial chain, a 3R serial chain.
In Ubuntu or in Linux it would work, right?
Yeah, 1, 2 or 2, 1 would work in this case.
Okay. We have to VI the file just. We just have to VI the files, means we just have to edit the files and
Yes.
How to run it.
You send it to me, I'll run it, because right now we only have it installed in my computer.
Okay.
So just edit your file with whatever text editor you like, and put there your number, send it to me, I'll run it, and I'll return you your solution.
I can try installing Artrix.
We are trying.
So it will be any special configuration that we have to install in that computer, or we can install it?
You can install it in yours if you want. It needs to be under Linux.
Yeah, I have it.
So yeah, you can try. The instructions are available in the web page, and maybe we should write a few instructions. Maybe we'll send an email with the instructions, because you need to install the MIMPACK, the C MIMPACK, which is the solver, and then Lua, and then the program itself. But in theory, it's fairly simple. We are getting some problems, so we are working on solving those. But yeah, if you have a computer with Linux, install it in your computer, and that way, the file that I'll send you back is just it just gives you the coordinates of the access. But when you run it in your computer, you will have a visualization of the actual. Very simple, but enough to have a first idea on how that works. All right. So maybe we should talk about that. What to install now? Yeah, let's do that. Let's talk about installing. So the Lua file. So C Lua file in Lua example in web page. And now we are going to talk on in Moodle page. Okay, and let us talk about Artrix installation for everybody. Artrix installation for dummies, that means for me, okay? Installation. Okay, and I'll need some help here. So first we install Lua. And is there any specific version? We are using just the last version, right? 5.2.2 latest. We the way we use it, it doesn't matter much. I mean, I think Edgar had to modify a few things, changing the version, and then we need to install the. Well, we need to have the libdq, right? Which is the.
For dual core.
I forgot what else. Is that in Edgar's page?
Yes.
Let me just go there. Come on. What is it? Oh, great. What is my Moodle? Did it disappear? Okay. Oh, I guess I closed it. I didn't realize. Okay. Let me just look for it. Edgar Simoserra. Source code, Artrix. Oh, libdq. Here it is. Okay, so we need to download this libdq. Oh. Which are, it's a library with dual quaternion commands that were defined. So yes, specifically to handle our algebraic objects. And then there, in that web page, there are some tutorials so that you can test if Lua is working fine. Okay, so you can test that. So before proceeding further, test Lua with example. Edgar also has a brief tutorial on basic Lua commands. Okay, so we have Lua. That's the first step, and then what else? Then we need to install the CMIM pack, right? Okay, the next one is the install CMIM pack. And the CMIM pack, we should be able to just Google it and it should appear, right? I don't know if there is a link here. It's not a link, right?
It should be a specific version of it.
Yes, and CMIM pack is this one, right?
Yes.
Okay, we need a specific version because some of the things we use, and that is the 1.1.3, right? So let me just write that there, so you can just Google it and it appears there, 1.1.3. At some point we may just, if we have time, we will look at what's the difference and we may modify so that we can install a higher version. But so far this one, and then the next one will be install the Artrix, right? Install the Artrix, get errors, let us know about the errors, right? So this is again in Edgar's page, which okay, so here it is, Artrix, okay? And here in fact you have the dependencies, so the libdq, the CMIM pack, Lua, some of the other things you may have. If you don't have them, then you'll need to install those too, okay? We had to change a couple of things while installing to make it work, but it may depend on each computer. So in principle, with this, that should be enough, right? And then test it. Test it.
That's the make one.
Yeah. Well, if it doesn't work, then it does not work. Then we'll need to edit the make file. And if it doesn't work, let us know and we'll give you additional instructions. That's very specific things that you may have to change in the make file. And then just test it. And of course all this is in Linux right now. We don't have a Windows version. So having a dual installation of Linux and Windows or something else, that is a good idea.
So does it matter the order of installation before?
Yeah, because Artrix depends on this, so it's going to look for them. Yeah. Lua and MIMPAC, they are not related, so it doesn't matter. But these two need to be before Artrix. I think. All right. So here is our whole process, and if we don't have a link, we will put a link to this page from our web page so that we know where all the software is. I don't think we have that yet, but we will put that. And here are some of the papers. Here our papers are also in our web page, so we can find that there. And that's it. So with this, we are ready to do the kinematic synthesis of almost everything. Is there any question? You want us to run one example, maybe?
We can get just by Artrix in Google or this website.
You cannot get that?
Yeah.
You will have to, if not, it's Edgar. The author is Edgar Simón Serra. Simón Serra. Now the next question is, okay, now you have been able to define your hand, you get the result back, which is basically, so your result will be just something like this. S1 equal to, S1 plus epsilon S1 0, S2 equal, and this will be 6 numbers, coordinates, right? So basically what I'm giving you is this. At a particular configuration of the mechanism, I'll give you the location of the axis. Okay, this is what you will get. Now, how do you create a hand from this? That's the next question. Right? I mean, the first thing that comes to mind is, knowing that I'll say it.
Common perpendicular.
No, but I mean, it doesn't come to my mind. The connectivity. So which joint goes before which joint, and so on, which joints are connected by a given link. So knowing the connectivity, you can just start by creating a common perpendicular line, and that will be your link, right? So imagine that S1 is connected to S2 because we have the graph, and then here we have the palm of our hand, so actually we have this. So you could create this kind of solid, right? And then you could create another common perpendicular, because this is connected to this is connected to this. So it will be the most basic implementation of your hand. This actually is a 2 and then 2, 2, right? Hand. What this means, if you translate this to a real thing, is you have a joint here, right? Another joint here. Kind of like this. You could create something like that. So this one is, and then you have this big linkage here. And here you have your end effector somewhere else. Somewhere in there is the position that you wanted to reach. Okay, so this will be, maybe it's not, doesn't have to be a line, it could be, and then this one is the one that is attached to whatever else we have. So doing the common perpendicular line and putting some joints there, you will have a first implementation of your system. This last link is not given by the process, but knowing where the first position is, you just need to join that first position, for each of the branches to the last joint. Okay. Usually this first implementation is not the best, it's not the optimal, and it looks very strange. Okay, so what we need to do is we need to decide where we want these links to be along our joints. So now it comes the second part, which is the design in detail. And this is what we will, some of us will be interested in doing. Some of other people will just leave that for the pure mechanical designers, right? But basically what we need to do is we need to realize that the links can be anywhere along the joints, okay? The links can be located anywhere along the joints, which means that if you have a joint here and then another joint there, you can have this simple link at the common perpendicular, something like this, but you could also have this link or this link. All of them will give you the same motion as long as they attach at some point of these joints, okay? Or you could have many different links. So what we need to do is we need to optimize those, and that's part of what GMSCare has been doing. So we can optimize that placement based on whatever performance parameters we want. The placement of the links. Based on requirements. They could be requirements in the overall size of the hand, on the many different things. So basically what we are going to be giving is, if these are the joints that we obtain from the synthesis process, we can there are many ways of doing it, but let's imagine that we will do it from the common normal. We can always compute this common normal. Is unique, right? It's a common normal line. You can give a point, an anchor point given by a parameter from that common normal point, for instance, okay? So you'll say, okay, my link will go from here, I'll put my joint here to maybe here, right? So you put here a T1, a T2. So here I'll put my second joint, and this is my ideal link because of this particular parameter I want to optimize, okay? So we can do that. We can do a second stage of optimization that gives you, once you have the joint access, it gives you the anchor points where your joints are going to be, kind of. Now we need to take this to a CAD system and draw it. And then CAD system. So we need to be able to import these points and then do the detailed drawing. And then once you have the drawing, you can create a prototype and so on, okay? And really, I mean, if we stop in the synthesis stage, we really cannot say if that hand is going to be good or not, okay? We need to go the further steps in order to see if that hand is going to be usable for what we want to use it, okay? So we have, for the optimization, we have some Mathematica notebooks that GMSCare worked on, and maybe we should post those also on the, we haven't posted them yet in the web page, right?
Okay. It's not posted.
Okay, we have to do that. We'll do that maybe this week. You don't have finals, right?
No,
you do have?
No.
Okay, so we will post the Mathematica files on the web page so that you all can use it. And then we also are going to have an easy way of importing this to SolidWorks. We will have some script to import to SolidWorks. So with that, we will have the process pre-automatized and pre-complete. So you select your topology, your position, run Rtrix. With the output of Rtrix, you run your optimization. The output of the optimization, you send it to SolidWorks, and it will give you a model that then you can modify further. All right. Okay. So let me give you, besides the one that we are working on, because I'm not sure that can be run in Rtrix, let me give you a